Hi there. So let's talk a little bit about the ideal gas law. And so what we're talking about is an idealized gas. So this isn't a real gas, but gases will behave according to it under common temperatures. And to build our model, we need to make our assumptions. So our first assumption is that the particles in this gas are separated by a great distance. And what we mean by that is that the particles are so small that relative to each other, this distance is very, very big, relative to the size of the particles. And these particles, they could be single atoms or they could be molecules, it doesn't matter. So I'll just refer to them as particles. So we have particles and there's a whole bunch of space in between them, so low density. That's our first one. Second one, any collisions between the particles, these things are flying around, we'll consider to be elastic collisions. Sometimes you'll read this and they'll say there's no collisions, but they're going to collide. We just say that they're elastic. That means that there's no energy loss. Remember, inelastic, then energy is not conserved, but elastic, energy is conserved, so everything's good. Next, third is that there's no forces acting between the particles. So these particles aren't attracting each other or repelling each other. That's different from a solid. In a solid, they're so close, the atoms or the particles are so close together that they pull and attract each other or push each other away. A gas, they're not. So there's no interactions between the particles, even when they collide. And then the final one is that the kinetic energy is proportional to the temperature. And this one we'll get into with kinetic theory. But the idea is that if we heat it up, these things are going to move faster. That's all it's saying. Okay, so if all of these are true, then what we have is we have an ideal gas. And the first thing that we'll look at are going to be the macroscopic properties. So we're looking at macroscopic. And these are the things that are obvious, so we can measure. Usually it means that we can see, but these are the big stuff that we can measure. And we have a few which are referred to as state variables, and that's going to be, so state variables. And that would be pressure, temperature, and volume. So pressure, temperature, and volume. So for a gas, these three, once we know these, we know exactly what's going on with the gas. They define it. And then there's another one that comes into play, and that's the actual number of particles that are in here. So we'll also have the number of particles. This is not a state variable. So number of particles. Okay, so you did an investigation, or you should have by now, and you were just looking at the relationship of all of these four. And that was using the PhET sim. Let me pull it up. So you're playing around with this thing. Let me pump some particles in here. Okay, so the first thing we might want to look at is like what happens with the volume. How does decreasing the volume affect the pressure? And we're going to hold temperature constant for this. So we see a pressure. I'm just let it stabilize a little bit. It's not going to stay exact, but it looks like around 26 kilopascals, 2600. So I'll do about half the volume. And look, the pressure jumped up. So it appears that when I decrease the volume, the pressure increases. And if I make the volume really big, the pressure drops. And so that would be an inverse relationship. And so we have pressure is inversely proportional to the volume. And the relationship between these two actually is a separate law. And what it says is that P times V is constant. It's some constant. Okay, and then we can look at, so that was pressure and volume. We could look at pressure and temperature. So let me go back. So I'll just leave it like this, and now we can just, where's my temperature? Oh, we want to change the temperature now. So we'll hold the volume constant, and I'll just heat it up, and we'll see what happens to the pressure. Okay, so as the temperature is rising, I can see the pressure is increasing. Yeah, so these are directly related. So a direct relationship, so pressure is proportional to temperature. And then we can also look at the number of particles. So I have a pressure, looks like it was around 41. So let's just pump some more in here. I can see quickly that the pressure jumps up. So more particles, we have greater pressure. So those are also directly related. So number of particles is big N. So pressure is also proportional to big N. Okay, so we can put all of this together into an equation, and that would be our ideal gas law. So we can write it like such. So P is equal to, I'm doing proportionality. Since it's proportional to all of these, I can just multiply all of these, and that would maintain the proportion. So it'd be 1 over V times T times N. Now the thing is that with a proportionality, there has to be some constant. Sometimes it's 1, but in this case it's not. And we're going to label it with a little b. So we have the pressure is equal to K times 1 over V times temperature times the number of particles. And I'm just going to rearrange. I'm going to multiply the V over because that quantity is a constant. So we get PV equals the number of particles, I'm just going to rewrite it, times KB times T. And this is our ideal gas law. So pressure and volume are clear, and temperature, remember, keep in mind temperature is always in Kelvin. This KB, that is Boltzmann's constant. Boltzmann's constant. And then N is the number of particles. And you're going to have to be careful with these N's because we're going to redefine the ideal gas law. But that's the number of particles. Boltzmann's constant is given on your equation sheet. I never remember what it is. 1.38 times 10 to the negative 23rd. So this is equal to, let me just pull this over here so you can see it. It's right here. There's Boltzmann's. So 1.38 times 10 to the negative third. And then here's our ideal gas law. So N, Boltzmann's constant, times temperature. And then now what we're going to do is we're going to change it over into the more familiar term, PV equals nRT. This N right here is different from this one. This is the number of particles. This is the number of moles. So let's go through that real quick. So moles, for those of you that have not had chemistry, 1 mole, your book will explain this, so read this carefully. It gets a little bit confusing when you first read it. 1 mole is an amount of substance, amount of something, whatever it is, something, which has the same number of particles So it has the same number of particles as 12 grams of carbon-12. So if we take 12 grams of carbon-12, it has so many particles. So if we take another amount of mass such that it has the same number of particles, that's 1 mole. So 1 mole, moles always have the same number of particles, and that number of particles is called Avogadro's number. It's called Na. And 6.02, I believe. 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd. And those are particles per mole. Particles in 1 mole. So a mole of any substance will always have this many particles in it, atoms or molecules, whatever they are. And so we'll use this then to change this, because the number of moles is just the ratio of the number of particles to Avogadros. So if I had 6.02 particles, well, that would be 6.02 divided by 6.02 times 10 to the 23rd on both, but that would give me 1 mole. If I had twice that amount, I would have, whatever it is, and so on. So we'll use this, and then we can rearrange this. So this would be N is equal to the number of moles times Avogadros. Now I'm going to take this and substitute it into our original ideal gas law, and we'll have a different form. So PV equals big N Boltzmann's times T. So PV is equal to this little n times NA times Boltzmann's times T. And then we redefine this. So we redefine Boltzmann's constant times Avogadro's number to be the universal gas constant R. nRT. So this is also the ideal gas law. So we have two. We have this one, and this one is when we know the number of particles, or we want to know the number of particles. So it's handy. And we have this one, which when we have the number of moles. So that's how you'll tell which one to use. It depends on what they tell you. But this is pretty cool though. So if I have a gas, I can just measure the pressure, volume, and temperature, and I can tell you how many atoms are inside of that gas. Pretty handy. But that's the ideal gas law, just kind of laying it out and kind of what you investigated. Next, we'll move into kinetic theory. So we'll really just dive into what we mean, what temperature really means. Because up to this point, we've just said that temperature is a quantity measured by a thermometer. It doesn't really have a whole lot of meaning. But now we'll get into the microscopic level, like what's happening.